Jeez, how many homework problems did I give you guys? I'm just kidding. Okay, so due to a manufacturing error, 3 cans of regular soda were accidentally filled with diet soda and placed into an 18-pack. Suppose that 2 cans are randomly selected from that 18-pack. Complete the parts A through C. Determine the probability that both contain diet soda. Okay. So you're okay here. So I'm thinking for this one, you would have what? There's 3 cans in there. So it'd be 3 and 18, 3 out of 18 times 2 out of 17. If you think about that. So you could do it with. So I'll just go through the whole thing real quick. Bum bum, maybe. So if we pull that up, for the two, it wants them both to be diet. So you think about, right? They can be either diet or not, and diet or not. So we want this branch right here, 2 diets. So the first one there was 3 out of 18 there. The second one there would only be 2 out of 17 left. So it would be 3 out of 18 times 2 out of 17. You can solve it that way. And diet versus diet complement. It's the complement. Yeah, it's not diet. In this case, it's regular, but okay. So what does that come out to be? I could pull up my calculator. 3/18 times 2/17. Anybody got that? I got 0.0196. That's what I get. 0.0196. Okay. Find the probability, determine the probability that both contain a regular soda. So we can go back to our tree here and we can see, go with our pen here. That's going to be this branch right here, both regular. So that would mean there was originally 15 out of 18 regulars, which means now if you selected one, there would only be 14 out of 17. So that probability would be 15 out of 18 times 14 out of 17. And what do you get for that? Any takers? I get 0.6863. 6863. Okay, cool. This part? Would this be unusual? No. This would be typically what we're going to end up using. But typically, anything that happens more than 5% of the time, we consider not unusual. Things that happen less than 5% of the time, we consider unusual. Typically, that's our sort of a rule of thumb. It's not like anything hard and fast, but I would say no, that's not unreasonable. That has like a 68, almost 69% chance of happening, so it's not unusual. So it'd be there. Now the first one would be a little bit strange, a little unusual. Determine probability that exactly one is diet and exactly one is regular. So that would be these other 2 branches, right? But we can kind of cheat a little bit here. So we had 0.0196, 0.6863. So this one was 0.0196. This one was 0.6863, right? So this is both cans are the same. This one is both cans are the same. So the only other 2 options are these 2 branches. But remember, probabilities have to add up to 1. So if the probability of them both being the same is, they could either both be diet or they could both be regular, then the probability of them being one of each is going to be 1 minus that probability. Because one of each is the complement of both the same. So we can take that away. So that would be 1 minus 0. I don't even want to guess. 7, but I'm guessing anyways. I don't want to guess. 7159?
7059.
7.059. Okay, which would be what, 0.241? No, 20. No, 2941. Is that right? 0.2941. Okay. So you take advantage of complement probabilities. Okay. All right. Yeah. All right. What else?
46.
Same homework.
Yeah.
46. Okay.
Oh, wait.
No? Yeah.
Never mind, it wasn't that one.
Okay.
Might have been 47.
Yeah. What else? Other ones? Well, we might run into it.
44.
So 44. Was this your one you were talking about? 47?
Yeah.
Oh, this one's hard. We're going to do an example like this. Okay, so just hold off on this one. There's
I tried following the example thing that popped out, and I tried doing it the exact same way, and I kept getting like.
this. We're going to go over a problem like this one. I think today we'll get there.
I would get close to the answer, but then it would just be
The easiest way to do this is we need to use some counting techniques that we're going to talk about today and tomorrow. Okay.
Number 19 and part 2.
Yeah. Someone had another question from this one real quick.
44.
44. So hold off on that one, okay? So you're talking about picking a card from a deck. What's the probability that the card drawn is a spade? And then now you're saying the second part, right?
Yeah,
So the first part here, it's just going to be the probability that it's a spade. Well, that's just going to be 1 in 4, right? So that'd be 1 out of 4. But it wants a decimal, doesn't it? So it'd be 0.25. Okay. The probability the card drawn from is a spade given that it's black. So once you eliminate all the red cards, you're only left with black cards. What's the probability of a spade? So if I only have black cards, what suits are left?
13.
Clubs and spades are left, right? Clubs and spades are black. So then, well, what's the probability of getting a club if I only have clubs and spades? 13 out of 26, or just 1/2, right? Half the cards are spades. So once you eliminate all the red cards, you're only left with the black cards, which half of them are clubs and half of them are spades. So then the probability of pulling out a spade, given that you have only black cards left, I think would just be half.
On the end, mine says given that this card is court. I don't know.
Given that it's what?
Court.
Cool.
Would that be one of the king cards?
What does that even mean?
I don't know. It's a face card. Like a
Yeah.
face card. Like,
Oh, given that it's oh, okay.
That's what I was confused on.
Oh, yours doesn't say black.
Yeah.
Yeah. Given that it's a face card,
Yeah.
basically. Yeah. Then I don't think that changes anything.
The same thing. It's just, yeah.
Yeah, but if it's a face card, I don't think your probabilities really changed, because out of the face cards, I think 1/4 of them are still spades. So I think your probabilities stay the same if that was your condition. Yeah, each one's a little different. Okay.
I have a question.
Yes.
Can we do number 37?
I hope so. Same homework, and then we're going to get to number 2 in a second.
Yeah.
Airlines failures can result in catastrophe. So what they do is they do redundancy. So that means that a critical component has 2 backups. So if a particular component has a failure rate of 0.028 and they have a triple redundancy, what's the probability that the system doesn't fail? Right? Okay. So you could use this as well. What I would do is I would think about what's the probability of failure, right? So the probability of failure, right? That means all 3. You have triple redundancies, so that means this has to fail, and this has to fail, and then the third one also has to fail, right? All 3 of them have to fail. So what's the probability that the first component fails? Well, that was 0.028. Was it 3.8 in yours? It might have been different in mine. Mine says 0.028. Yours will just be a little different, but same process. So this one can fail at a rate of 0.028. This one's going to fail at a 0.028 rate, and this one's going to fail at a probability of 0.028. Each of these are independent. Okay, they don't have if one fails, it doesn't change the probability of the second one failing because each component's just put in place. They all have the same rate of failure. Ooh, there you go. And so then the probability of failure is just going to be 0.028 times 0.028 times 0.028. Ooh, my marker is freaking out. Easy there, Tiger. It's possessed. That's only going to be mildly annoying. Okay. So what does that come out to be? I think it's because of the way I'm. What does that come out to be?
0.0002195.
Like that? 4 zeros?
Yeah.
Okay. Oh, cool. All right. It's back. What is it even doing? Like, I don't even understand. Oh, I know what happened. All right. So this is the probability of failure. So then the probability of non-failure, right? It's going to be 1 minus 0.0000219, which is going to be 0.9999785.
Which that's the complement. Is that
What do you mean?
like the 1 minus
Yeah.
the answer you got is the complement?
It's the complement, yeah. Because success is the complement of failure.
Okay.
And that's what we were looking for, was probability that the system doesn't fail. So 8 decimal places. So what did we get? 0.9999 something 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 7805. Yeah. Okay.
Can you go back to the last page real quick?
Well, this right here. Yeah. Yeah. So we calculated the probability. Probability of failure is a little easier because to succeed, just one of them has to stay alive. It doesn't matter if 2 of them, crap out on you because you have that third one in place. So the probability of success is really, really, really high here. All right. So first get probability of failure, then use complement. Well, that's not where I wanted to go. So let's see. The minimum number of currents. So they're talking about this threshold here, right? So what they want to do is they need to figure out, well, if you wanted to get it down to 0.99999999999, right, of not failing, they want to know how many components you would need. So you could do this a couple ways, but one way you could do is just guess and check. So like for example, if I'm trying to get here, I need to get my probability of failure. Well, my success. I need to get my probability of failure less than 1, 2, 3, 4, 5, 6, 7, 8. I think that was what they said, right? So, wait, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So I need to get my probability of success down, or my probability of failure down to that, right? If I want my probability of success to be 0.99999. So what you can do is you can just say, okay, well, each time you add a component, the probability of failure just goes up. So we saw to the third with 3 components, and that was equal to 0.0002195. So then you can try it with 4 components and see what your probability gets down to. You could guess and check. So that would be, I don't know.
I think it's 5.
Let's see, yeah. I'll try this one first. So 0.028 to the 4th. That gets it down to 0.02345 zeros, 6, 1, 4, dot, dot, dot. So that's not low enough yet. So then just keep trying until you get something below the threshold. And that's how many components it's going to take. Okay. So 4 is not quite enough. We apparently need to go lower than that. All right. Good question. All right. What else? Yes, I've not. Part two. Part two. You said 19? Grade appeal process. A jury has to be 5 individuals from a pool of 9 students and 11 faculty. What's the probability of selecting all students? Yeah, let's wait on this one. This one also involves some counting. Yeah, we need some counting strategies for that one. We're going to talk about that hopefully today. Any other questions? Yeah? Same question? Same homework assignment? Yeah, that could also be, that's probably a counting problem. Yeah, so hold off on that one. We're going to cover some of that counting stuff by today, I think. All right. 30. Is it the same problem? How homework? Yeah, anything on homework too, I think we need some counting strategies for. So we're going to cover those today and tomorrow, okay? So let's hold off on those at least until tomorrow. We get some of the counting stuff out of the way. Okay, anything else? Yeah.
I have a question about the activity.
Yeah?
So when you like roll a 2, is it like you're actually rolling a 2 or are you rolling 2 ones?
No, like rolling a 2, like a 2 pops up on the face.
Okay, that's
Yeah, yeah. All right. Okay. So, let's see what we can get ourselves into today. All right. So this is, so here we talked, last time we were talking about independent events, right? And what it means to be independent. Independent means that the probability of one doesn't affect the probability of the other. Okay. So we have the definition. There is this nice special multiplication rule if you have independent events, and that's what I was doing with those failure rates. So let's say that A and B are independent. Okay. Then if you want to calculate the probability of A and B, then it's just going to be equal to the product of the probabilities if they're independent. Then you can calculate the probability of both happening by multiplying them. Okay. This only works if they're independent, though. If they're dependent, then we need to maybe use like a tree diagram or something, because the probabilities change from trial to trial. But as long as they're independent, we can just multiply straight across. And that's like what we just saw with the components failing. So one component is independent from the other component is independent from the other component. So the probability of all of them failing would be the probability of each one failing separately, and we multiply them. Okay. So I'll give you another example here. So first, you just have to decide if they're independent or not. So let's say we're talking about a roulette wheel. So in a roulette wheel, you have 38 slots, right? And 2 of them are green, and 36 of them alternate between red and black and have the numbers 1 through 36 on them, right? So there's 38 slots total, 2 green, 18 red, 18 black, and they have some numbers in them. And you can make all sorts of bets in roulette. You can bet on single numbers, you can bet on colors, you can bet on multiples of 3 or what. You can bet really however you want, okay? What's that?
Bet on a third of the wheel is on.
Yeah, you can bet on they have different words for that. I don't know all the terminology, but yeah, there's lots of ways to bet. And so if you're going to play, let's say you're going to play roulette 3 times, what's the probability that you land on green, then you land on red, then you land on a multiple of 3? That's what I want to know. Okay. So are each of these events independent of each other? Is each roll independent?
Yeah.
Why? How do you know?
Doesn't matter what you land on first, the other 2 are still going to have the same percentage chance.
Yeah, because a roulette wheel, it doesn't know that it landed on a green last time or whatever, right? It just every single time you roll, your probabilities are the same. So you would say that each of these are all independent. I'll say independent plays. So then the probability of, say, getting a green and then getting a red and then getting a multiple of 3, right? Since all 3 of these events, green, red, and multiple of 3, are independent, then we can just take the probability of green times the probability of red times the probability of a multiple of 3. And that would be our ultimate answer. So if you have probability of green is what? What would be the probability of a green on this roulette wheel?
2 and 38.
Yeah, so there's 2 green slots out of 38 total. How many, what's the probability of red?
2 out of, or 30.
So you have 36 that alternate red, black.
17 out of 34.
Close. Half of 36 is 18 out of 38. Yeah. So 18 of the slots are red out of the 38 slots. Okay. And then what's the probability of a multiple of 3? How many multiples of 3 are there between 1 and 36?
Well,
There are 12. Yeah. Well, 36 divided by 3 is 12, but yeah, it works. So 3, 6, 9, 12. Add them all up, there's 12 of them. So there's 12 ways to get a 3 out of 38 slots. And so then the actual probability of this occurring is you just multiply those all together. And what do you get as a decimal? Let's round it to, say, 4 places. What do you get? It's going to be low. It's going to be something small. I mean, it's like around 1% or something like that. Or less than 1%, like 0.001 or something. 0.007, 7, 8, a 9 if you round. Yeah, close enough. There's more there, but okay. Yeah. So as long as they're independent, you just multiply straight across. Yeah. And notice, unlike when we were picking people up without, unlike when we were picking people up before, our denominator doesn't change here, right? Because each time we roll, there's 38 options. It's not like when you roll a number, you can't roll it again next time. Okay, so independent versus mutually exclusive. What's the difference? What does mutually exclusive mean? Exactly. Mutually exclusive. They cannot happen at the same time. It's not possible. What does independent mean?
They don't affect each other.
They don't affect, one doesn't affect the other as what? In a way, but more specifically, it doesn't affect its probability. Yeah, yeah. So it's a statement about probability. So independent means one event doesn't affect the other event's probability of occurring. Okay. So they're independent if knowing one doesn't affect the probability of the other. But they're mutually exclusive if they can't have it at the same time. Are mutually exclusive and independent the same thing? They're not? Are you sure?
In the homework
It said no. That's right. They're not the same thing. So if I ask you, for example, like, hey, are these the events independent? Why or why not? Don't tell me that they're independent because they can't happen at the same time. Because that would be mutually exclusive, right? So don't do that. They're two different concepts, and independent doesn't mean mutually exclusive. So don't put that on an exam. And I'm going to tell you not to put that on an exam, and someone in this room is going to put that on an exam. And I'm not going to be happy with that person. Okay? Independent is not mutually exclusive. Okay? Someone's going to do it, though. Don't be that person. Don't be that person. Don't be the person that tells me independence means they can't happen at the same time. Okay? Don't be that person.
Would you somehow word both definitions in the answer to the extra point?
Well, what? How would you? Maybe. No. I don't know what that means. I'm not really sure.
At the same time because the events affect the probabilities of the outcome.
That's not true. Mutually exclusive events.
Yeah, but if I'm doing independent, that can be true.
Mutually exclusive events can never be independent. Never, ever, ever. Because think about this. Mutually exclusive means they can't happen at the same time, right? So if I tell you this event happens, what do you know about this event? It definitely didn't happen. So in fact, if they're mutually exclusive, they're like the opposite of independent. Because telling you one happened necessarily means this one definitely did not happen. Couldn't happen because they're mutually exclusive. Yeah, so they're kind of, it's almost like, you know, it's like the antithesis of independent or something. There is one exception, of course, but it's trivial and we're not going to talk about that. Yeah, because if one event has a probability of 0, well, but then they're uninteresting because that means it can never happen. But anyways, yeah. So mutually exclusive and independent are different. Okay, so I'll give you an example. Let's say that you're drawing a card from a deck. So say that the event A is that the card is a king, and B is that the card is a heart. Are these two events independent, and are they mutually exclusive? So first off, one of these is easy to answer. Are they mutually exclusive?
No,
No, why not?
because you can have a king that's a heart.
Exactly. You can draw a king that's also a heart. Yeah. So they're definitely not mutually exclusive. Now, are they independent? Right? Are they independent? So think about this in this way. So let's think about what is the probability of A.
4 and 52.
There's 4 kings out of 52 cards, which would reduce to 1 and 13, right? 1 out of 13. Now, what would be the probability of A given B, though? So this means given that the card is what? Yeah. So given that the card is a heart, what's the probability that it's a king? Well, there's 13 hearts, and only one of them is a king, right? So if I tell you that a card is a heart, did I actually change the probability of that card being a king?
No.
No. It's like I didn't give you any useful information, right? I picked a card and I said, hey, you want to bet on a king? And you say, I don't know, give me a hint. And I say, oh, it's a heart, right? Well, I didn't actually help you make a decision because your odds of winning are still the same here, right? And the same thing works the other way. If you look at the probability of B, what's the probability that you get a heart? Well, there's 13 hearts out of 52 cards, which reduces to 1/4, right? And if you look at the probability of B given A, right? So this is given that you have a king, right? So if you have a king, you only have 4 cards to pick from. And how many of them are hearts? 1 of them. So I'm not helping you. So they're not mutually exclusive because you can definitely have the king of hearts. But they are independent because telling you one happened doesn't actually affect the probability of the other happening. Okay? So independent, not mutually exclusive. They are not the same thing. So don't tell me they are. All right. Cool? Makes sense? Yeah. So independent is kind of like saying one doesn't really give you any information about the other. All right. Now, this is where we're going to get in. Now we're going to get into some of the stuff that's going to help you answer some of those questions that I told you I didn't want to answer today. But we'll have some counting strategies now. I'll handle them. So I forgot to put my section numbers here, but we're getting into this our section on counting. So let's say that you have, and if you came out in 94, some of this stuff's going to look familiar to you. And so you get this car manufacturer. They got 8 models of vehicles they sell. Each vehicle comes with 4 trim lines, and each car can come in 9 unique colors. So how many unique vehicles can the manufacturer make, if this is the case? How would you solve this problem? You just multiply the numbers together, and why would you do that?
Because you can put them in each bucket, like individually.
Yeah, you could do slots. Sometimes people do. You could think of it as a really big tree diagram, which you don't actually want to have to draw. But you could think about like 1, 2, 3, 4, 5, 6, 7, 8 cars, right? And from each of those cars, you can pick 1, 2, 3, 4 trim lines. And from each of those trim lines, you could make like 1, 2, 3, 4, 5, 6, 7, 8, 9 right? And you can see this thing's gonna like, this thing's gonna blow up to a really big tree. But how many branches are you ultimately gonna make? You're gonna make 9 times the split of 4 times the split of 8, right? And so ultimately there's some big number, and I don't know what that number is. Somebody help me out. 288? 288 unique vehicles are possible under this scheme. Okay? 288 unique vehicles. This is something that we call basically, I don't know, every book calls it something different. I just call it the basic counting rule, okay? So the basic counting rule says if you want to know how many ways events can happen at the same time, right? Where, let's say you have like event 1, maybe event 2, event 3, and so on, right? So if event 1 can happen n ways, and event 2 can happen m ways, and event 3 can happen k ways, or whatever, and ... then the total number of possibilities is just going to be, n times m times k times ... Okay, so you just multiply straight across. This can happen this many ways, this can happen this many ways, this can happen this many ways. So total, it can happen the product of those numbers of ways, right? And conceptually, you can just imagine this tree diagram just like blowing up into a whole bunch of branches. Okay, so this is a basic counting rule. And it's applicable in a lot of situations, but not all situations. All right, I'll give you another example. So you just multiply them together. So let's see, talk about Washington State license plates, right? So in our license plates, you have 3 letters, 4 digits. And as far as I know, there's not any rules, but maybe there are, but who cares? I'm pretending there's not. And so the first 3 have to be letters A through Z, and the last 4 have to be numbers 0 through 9. Then I want to know how many unique license plates can be formed in the state of Washington, right? So I just make slots sometimes, right? So like these 4 have to be digits 0 through 9, and these 3 have to be letters A through Z, right? Okay, so how many ways can you pick your first letter? There are 26 letters in the alphabet, so there's 26 ways to pick that letter. How many about this one? 26? How about this one? 26? How many digits are there? 10? 10, right? So then the total number of plates that we can form here is going to be 26 times 26 times 26 times 10 times 10 times 10 times 10, which would come out to be, how many unique plates can we form in the state of Washington? Somebody give me that number.
Wouldn't it be like 26, 25, 24, and then 10, 9, 8, 7?
No, because you can have repeats in this scenario.
Yeah, I believe in Washington State you can have a letter can pop up more than once, and so can a digit. So like your letters could be AAA. That could be the first 3 letters of your plate. So A can pop up more than once, and your numbers could be like 1111 or something. So numbers can repeat. Yeah, you're getting at a different concept, which we're going to visit in a second. Yeah.
175,760,000.
Nice. There you go. So, I don't think we're going to run out of license plates anytime soon. Right? There's only about 8 million of us here in Washington, so we got a little while. Yeah, we'd all have to own quite a few cars. Yeah. So I think we're okay right now. Especially because this is just like regular cars. This doesn't count like commercial cars or I think trucks have different plates on them and stuff too. All right, lots of plates possible. Now this is, you'll notice this is, and this gets at what you mentioned here. This is the concept you were referring to is a concept of whether or not your options have replacement or don't have replacement. Okay, so the idea is imagine you're going to just like randomly pick a license plate number, and so you just have like a bunch of, you have a bowl and you have 26 pieces of paper in it, and one of them is A, right? Well, you can pull out that A and put that on your license plate, but then you get to throw the A back in the pot and you can pick it again, right? So we call that with replacement, meaning that repetition is allowed. Okay, so if you're allowed to pick something more than once, then that would be with replacement. It's like you throw it back in the pot and you get to pick it again later if you want. On the flip side of that, without replacement, okay, that just means that values can't repeat. So the license plate example, replacement was allowed because once you pick a 7, you get to throw that 7 back in the pot and you can pick a 7 again later.
So this is thinking for, like, would that the replacement be for kind of like a combination, like a locker combination or a phone combination?
Yeah, so maybe like in a locker combination if you can't pick the same number more than once. Yeah. We'll see an example here without replacement too. Okay. So here's an example is that I have a box, say I have a box and I have 9 textbooks. How many ways can I rearrange 9 textbooks on my bookshelf, right? So you can start the same way, 1, 2, 3, 4, 5, 6, 7, 8. Let's say I have 9 slots on my bookshelf, right? But what happens when on my first slot, how many books do I have to choose from?
9.
Well, I have 9 to put in that slot, but what happens now? Yeah, am I going to throw that book back in and then allow myself to repick it later? No, I'm going to be sitting here picking out books and throwing them back in the box for the rest of my life, right? So once you put that bookshelf on there, you have 1 less book to pick from. So this one only has 8. Now I have 2 books up there, so I only have 7. Then I'll only have 6 books to pick from, then 5, then 4, then 3, then 2, then finally, at the very last slot, I only have 1 book to pick from, right? No options. Okay? So since I can't replace my books, I'm starting to run out of books to pick from as I put more and more on my shelf. So then the basic counting rule says that the number of rearrangements is just going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And what would that be? 362,880. Anybody else get that? Yeah. So if replacement's not allowed, you start running out of options as you pick more items out of there, right? You don't have as many options. Okay? Does that make sense the way I counted those options? All right. We have a nice notation for this because we run into this a lot in counting and probability. So we have this notation of factorials. So what we just saw, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We shorthand that into what we call 9 factorial. Okay? Yeah? This button is on your calculator. And it's normally locked away in like a PRB menu. Some people have it as an option. Just depends on what calculator you have. If you have the TI-30s, it's in the PRB menu. If you have a graphing calculator, it's in the math menu. And then in the math menu, there's a PRB menu that you can scroll to. But it's in there, okay? The PRB stands for probability. And in general, right, in factorial is just that number multiplied by every number below it. You know, times 3 times 2 times 1. So it just means take that number and multiply it by every whole number that's less than that, all the way down to 1. Okay? All right. And as a rule, 0 factorial we define to be 1.
But your equation is confusing.
Which one?
The middle one.
Yeah? In factorial?
Cause it's minus
I
one,
don't know
minus
why
two, and then it's
the way
goes
you
back
sound
down.
made it more confusing.
Okay, so the simple explanation is just take that number and multiply it by every number that's smaller than it.
Oh, yeah.
Yeah.
Okay.
But this is just a mathematical way to show that. Like, say n is 10, then 10 minus 1 would be 9, 10 minus 2 would be 8. But the rule, basically what it means is, every number below it. And from a practical standpoint, what it means is put 9 in your calculator and then go find the exclamation point and put that in there and then hit enter. But you can always get it by multiplying all the numbers below it. All right? And 0 factorial is always 1. That could have a non-intuitive or an intuitive interpretation, or you could just remember it. But, all right. So sometimes, though, we don't have room for all our options. So let's say that we're looking at the same example. So I have a box with 9 textbooks in it, but I'm running out of room on bookshelf. I only have room for 4, right? I can only fit 4 books up on that shelf. So now, how many ways can I pick and arrange those 4 textbooks out of the 9 on my shelf? Okay.
Doing the same thing with 4.
Right, so now, instead of having 9 slots, I only have 4 slots to shove them into. Now, of course, how many books can go here?
9.
Well, I got 9 books I could put there. Of course, now I've picked one, so now I have 8, 7, 6. And we can multiply this down, right? So then what would you get for that? 3024, 3024? Oops, 3000. It's supposed to be a 3. 3024 ways. Right, we ran out of options. Now, one thing to, where am I going here? So one thing, we could actually rewrite this, and bear with me for a second, right? So that 9 times 8 times 7 times 6, we could, if we wanted to. You don't have to necessarily write this down if you don't want. Couldn't we write this like this? Could I write 9 times 8 times 7 times 6 as this over this?
Yeah, but then
Sure, it could.
it also
Yeah, because notice the 5s are 5 over 5 is 1, 4 over 4 is 1, blah, 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 blah. Those all cancel. But I could use this and rewrite, because the top here is 9 factorial, and the bottom is 5 factorial. Is that true? Yeah?
Yeah.
And then we could even rewrite the bottom. Isn't not 5 just 9 minus 4? Right? What was 9 in the context of our problem? Wasn't 9 the number of books? And what was 4? The number that we could pick, right? So the 9 was the number of books that we could pick from, and the 4 was how many books we were choosing out of that. We were going to pick out of that and rearrange. Okay? And it turns out this general form of rearrangements will always be true. Okay? And this is actually what we call permutation. We have a special name for this. Okay? So if you're looking for the number of ways, and this is important, to rearrange, say, R items out of N total, okay? So you're going to pick up a certain number of items out of a certain collection of items, and you want to look at how many ways they can be rearranged. Then we call that a permutation. The notation we use is this NPR. That button is also in your calculator. But you can also derive it formulaically. It's always going to be n factorial over n minus r factorial. Yeah. Okay. So, like in the last example with these with the book example, you could actually go in on your calculator and put 9, then go find your NPR button, and then put in 4. And your NPR button is in that same menu that your factorial button's in. And if you hit a 9, go get your NPR button, then go get your 4. You should be able to, that should come out to 3024, just like that. You can check it. But, okay? Yeah.
Is it okay just to do it that way?
Yeah, sure. Mhm.
Just put the answer on
Yeah.
the list or something?
Yeah, that's okay. All right.
Try like 9 NPR on the test.
Well, that's how you would put it into your calculator. Technically, we would write that as 9p4 is how we would write it. But this is how it would have to go into your calculator.
Do you want us to write 9 permutation 4 on the test, or you just want us to write the answer if we use our calculator?
I'm happy just with the answer.
Okay.
If you give me the right answer, I assume you did not cheat to get it. All right. Yeah, so there you go, permutations. And the key here is we're talking about rearranging a certain number of items. Okay. So here's another example. So in the Olympics, there's a 4x400 relay, and there's 8 countries that participate. And in the Olympics, the top 3 finishers get medals, right? So you get gold, silver, and bronze. So 3 people are going to get medals, and they're all getting different medals depending on their order. And there's 8 teams participating. So how many unique ways are possible for the awarding of those medals? So what would this? How would we solve this here? Yeah. So our end here, we've got 8 teams to pick from. Only 3 of them can get medals, and the order they finish in is important, right? Because you'd really rather finish first rather than second, and you'd rather finish second rather than third. Okay. So then this is going to be 8p3. You can plug that into your calculator if you want. 8 NPR3. They're really not that hard to do by hand, because by formula here, right, that would be 8 factorial over 5 factorial. But 8 factorial is just 8 times 7 times 6 times 5 factorial would take care of all the other stuff, and your 5 factorials will just cancel. So we would just end up doing 8 times 7 times 6, which should match whatever you got in your thing if you did it by hand. 336. 336. 336. Yeah. So that's the same thing you should get if you go do in your calculator. Okay? So it would be advantageous to figure out how to calculate these in your calculator. It'll save you a little bit of time. But it's not impossible without them. All right. So if you have a certain number of items, you want to pick up some of those and rearrange them, that's a permutation. All right. Any questions on that so far? Right? Any questions about that?
So for permutation, order matters.
That's right. Yeah, you're rearranging things.
Yeah, it's the same thing. I was
Hmm?
going to say, so it
Mm-hmm. That's right. So the order with which things get picked is important for a permutation. So that's not always the case. So order's not always important, and we have to make that distinction. So here's an example. Let's say I have 30 students. I'm just going to pick 4 of my students to take a survey about my stat lab or something. Now, how many unique samples are possible? So when I'm taking a survey of 4 students, does it matter which order that I pick that student in? No, it doesn't, because let's say we have 4 students, A, B, C, and D, right? Well, if I would have picked that C, A, D, B, right, didn't I still end up getting the exact same 4 students in my survey, right? And you know, there's tons of different ways you could rearrange those 4 students. Now, in a permutation, these are all unique rearrangements if we're talking about permutations, right? Those are all unique. But I don't want to treat them as all unique, right? I want to take all of these and I want to say, no, those aren't unique samples. Those are just reorderings of the exact same sample, and I don't really care. I want to condense all of those into a single sample. And so what we do is we combine into one sample, right? Well, how many of these are we going to have to condense? Because if I have 4 students, how many ways can I rearrange them? 4 times 3 times 2 times 1 ways, right? So there's 4 factorial ways. So these 4, what does that end up being? 24? So for the same 4 students, there's 24 ways for me to rearrange them. But I don't want to treat all 24 of those as the same. I want to just combine them and say all 24 of you're the exact same sample. Boom, 1. And then okay, so this is the idea. So what we can do is, if it were a permutation, if the rearrangements were unique, this would be fine. We would just say, well, that would be 30 permute 4, right? And that would be 30 factorial over 30 minus 4 factorial. But now what I'm going to do is I'm going to divide out my combinations, because each one has 4 factorial ways of being arranged. So I'm gonna divide out an extra 4 factorial, because that's how many ways each of those samples could be rearranged. So I'm gonna divide that out so that those people all get treated as one sample. All right. So this is what we're gonna actually compute. Okay. And what do you get? So this would be 30 factorial over 4 factorial times 26 factorial. What do you get if you try that out? Anybody want to do that for me real quick? You have to put the bottom in parentheses, right? You could do it by hand. It's not too bad. Because it would be 27. The 26 factorials would cancel. And you would just have 4 times 3 times 2 times 1, right? So what do you get here? 6 divides into 35 times, 4 goes into 28 7 times. 27,405. Okay. But this actually, you notice the pattern here is that, remember, there was 30 students I'm picking from, and I'm grabbing 4 of them, right? And so when I don't care what order my sample gets picked in, this is an example of what we call a combination, okay? So we say that the number of ways to choose, say, are items out of n total, when their order is unimportant. Okay. We call this a combination, so we use NCR, and it's n factorial over r factorial times n minus r factorial, or there's also a combination button in your calculator. Okay. So on that last example, right, in your calculator, you should be able to go put in 30, go find your NCR button, and then type in 4, and then you should be able to get the same number that we just got in the last example. All right, so we are out of time, but that should help you with some of those counting problems. And then tomorrow, oh, excuse me, we're going to learn how to use counting to solve for probabilities. And then we'll be ready to go. Oh, I did post up the practice test, though, by the way. Thursday. So, right, our next test is coming up Thursday, and the practice exam is there now. So you can take a look at it and work on that, okay? Test on Thursday, and we're only going to go through this chapter 5 for this test. Just like last time, yeah.